The next unit we're going to do is curve sketching. Now there's quite a bit in curve sketching. Go on and get your pen out and go on and write all of this down. I know some of it's a little bit redundant, but guidelines for analyzing the graph of a function. The first thing you need to do is determine the domain and range. Then you need to find all intercepts, asymptotes, and symmetry. You need to locate the values for the first derivative and second. Where are they 0 or where don't they exist? And look at those for critical points. And then use all of your results to find the local extrema and points of inflection. This is a little bit more detailed list here, but the only way to do these is to do them. So let's just jump in. Let's look at the rational function 2 times x squared minus 9 divided by x squared minus 4. Now, all right, I'm going to assume you can do the derivatives. All right, so let me just go ahead and put them down here. F prime is 20x divided by x squared minus 4 squared. All right, and I'm going to go on and give you the second derivative as well. This is very straightforward to find, and then we'll start the analysis. It's 20 times 3 x cubed plus 4. Let's see if I can read my handwriting here. Divided by x squared minus 4 cubed. All right. What order you do these in isn't incredibly important. Let's see, I'm going to go and put in some axes here because I know this is probably going to be pretty symmetrical with respect to the origin. You don't want to waste your paper if everything's over in the first quadrant. But the domain is all reals except x equal 2 and negative 2. All right. When x is 2 and negative 2, you know you're going to have a vertical asymptote. So I can go in and put those in. Go and put in my vertical asymptotes. All right, plus 2 and negative 2. Now, do I have a horizontal asymptote? What's the limit as x goes to infinity of y? I see it becomes 2. So I can go on and put in a horizontal asymptote of y equal 2. Then you do need to label these. So I have a horizontal asymptote at y equals 2. All right, let me switch paint colors. Let's find our x-intercepts. When are they going to cross the x-axis? Well, that's going to be when y is 0. Let's see, where is y 0? Y is 0 when x squared minus 9 is 0, or when x is plus or minus 3. So, when x is 3, y is 0. When x is negative 3, y is 0. Now, whoops, that's a 0. You can go on and put those points in. So it's negative 3, 0, positive 3, 0. All right, what's the y-intercept? Y, when x is 0, is 2 times negative 9 divided by negative 4. So it's 2. So this is negative 9 halves. All right, so my y-intercept is x is that negative? Nope, that's positive. It's positive 4.5, 0. So I can go and put in that point. 1, 2, 3, 4, 5. All right, now I've got these asymptotes, and I've got my where it changes axis. So now let me look at my first derivative. Where is my first derivative 0? And my first derivative is 0 only when x is 0. All right, so there's one of my critical numbers. So when x is 0, y is, we already found this out, 4.5. And that's the only time the first derivative is 0. All right, let's look at the second derivative. Let me change pen colors. When is the second derivative positive? Let's see. Well, the second derivative, I'm going to put it over here, is negative 20 times 3x cubed plus 4 divided by x squared minus 4. Where is this positive? Well, the only time it's going to be positive is when the numerator is negative, and, well, hold on, it's when the whole thing is negative. Excuse me, the whole thing is positive. So if x is positive, all right, then this is going to be negative. If x is positive and greater than 2, this is going to be positive. So this is going to be negative when x is greater than 2. So f prime, double prime, is negative when x is greater than 2. What about when x is less than 2? Because I'm seeing a bit of symmetry here. As a matter of fact, I can see it should be symmetrical with respect to the y-axis because I put in negative x and I should get the exact same function out. So I know it's symmetrical with respect to the y-axis. So whatever I find for the first half, I should be able to find for the second half. All right. So when x is greater than 2, it's concave down. So it's going to do this right here. All right, it's got to stay concave down. All right, there's no more inflection points, and that should be a nice smooth curve. By symmetry, this should be the same. What about when x is less than 2? Well, what do we have? The numerator is going to be negative, the denominator is going to be positive, so the second derivative is positive. So this should be concave up. You don't have to absolutely fill everything in. It turns out, there are no inflection points. We did the test intervals verbally. Okay, you give it a go, stop the video, and start it back up when you're done. Let's look at radical functions. Radical functions are a lot of fun, and you also need to be careful with them. Okay, I'm going to go on and give you the first derivative is 2 divided by x squared plus 2 to the 3 halves. And we see that this is always going to be positive. You can't have this be negative. The second derivative is negative 6x divided by x squared plus 2 to the 5 halves. So I know it's always increasing, but I realize I'm going to have an inflection point, and that inflection point is going to be when this is 0 and f double prime is 0 when x is 0, So let me look at the negative infinity to 0. Let me look at what happens when x equals 0, and then from 0 on to infinity. I know the function when x is 0 is 0. The first derivative is, 1 over square root of 2, and the second derivative is 0. So I know this is an inflection point. When it's between infinity and 0 and infinity, I see that the first derivative is going to be positive. So it's increasing. And let's see, the second derivative is, that's going to be negative. So it's concave down. Between negative infinity and 0, I know that, let's see, the first derivative is positive. And the second derivative is positive. So it is, again, increasing and concave up. Let me take the limit as x goes to infinity of this, and I get when I do it from the positive infinity, I get plus 1. When I take the limit as x goes to negative infinity, I get negative 1. So I have two asymptotes, one at plus 1, one at negative 1. All right, so I'm going to put my 1 and negative 1, 1, 2, 3, 1, 2, 3, 4. And here are my asymptotes. I have the point 0, 0. And then it's going to go like this. Oops, not supposed to cross your asymptote there. All right, when you have radical functions like this, you do the exact same thing. You just need to make sure you check your inflection points. I want you to go on and give this one a try and put it in your notebook. Did you get it? Now, what do you do when you have polynomial functions? A lot of you are going to think polynomial functions are really much, much easier, and in a lot of ways the derivatives are. First thing I want you to do is go and take the first derivative. So this is 4x cubed minus, minus 36x squared plus 96x minus 64. Now I'm going to go on and factor this for x minus 1, x minus 4 squared. Why? Because I'm going to be looking for zeros. This is 0 when x is 1 and x is 4. The second derivative is 12 x minus 4 times x minus 2, and it has zeros at x equal 4 and x equal 2. Let's find our intercepts. When x is 0, y is 0. All right, and if we look at this, if I were to factor this, I would find I have another intercept at 4, 0. I have no vertical asymptotes. I don't appear to have any horizontal asymptotes. The limit as x goes to plus infinity, plus or minus infinity, is plus infinity. It doesn't matter which way I go. So, let me look from negative infinity. I know my second derivative is going to be positive. My first derivative, is negative. So it's decreasing and concave up. At x equals 1, f of x is 27. It's actually negative 27. The first derivative is 0, of course. Oh, but the second derivative is positive. So this is actually going to be a relative min between 1 and 2. I know the first derivative, let's see, that's positive, and so is the second derivative. So this is increasing and concave up. At x equal 2, again, another one of our critical points, f is negative 16. The first derivative is positive, and of course the second derivative is 0. So this is an inflection point between 2 and 4. I've got a positive first derivative and a negative second derivative, so it's increasing and concave down. And finally, at x equals 4, I have everything is 0. So this is another inflection point. Finally, between 4 and infinity, I have a positive first derivative, positive second, so it's increasing and concave up. All right. So, now we know an even polynomial is just going to keep going up. So let's do our little graph here. And we're going to see, what are my points? 0, 0, 2, 3, 4, 0. And it's going to continue going up like this. I know I've got a relative min at 1, negative 27. And so it's going to go down like that and then continue going up. give these a go.